Hello everyone, I'm Taewon Kim from Team 5 and we will give a presentation about final results of our term project. Our target paper is traversable ground and above ground segmentation using graph representation for 3D LiDAR scans. This algorithm proposed two novel graph structure-based modules for point cloud segmentation named as Travel. Also, Travel consists of a traversable ground segmentation and above ground object segmentation, which are graph search-based segmentation methods. I'll briefly introduce about related papers to our selected paper Travel. Point cloud segmentation algorithms are usually divided into three types: single-step approach, two-step approach, learning-based approach. Among them, Travel algorithm is point cloud segmentation of two-step approach. TGS is ground segmentation and AOS is object segmentation. Similarly, there is a paper about segmentation algorithm of two-step approach. GPF module for ground segmentation and SLR module for object segmentation works in an order for this also. PCA-based ground segmentation technology of GPF can run in real time. However, as you can see in the figures, it cannot show robust performance in terrain that has a lot of slopes. Even though the ground data is estimated good enough, due to the SLL algorithm, oversegmentation occurs frequently. This research can replace the ground segmentation. Unlike the previous research, it can do the ground segmentation through RANSAC-based planar modeling. As shown in the left figure, it divides its surrounding area into four quadrants, and the ground modeling is performed considering the continuity between each quadrant by dividing it into several sections. However, it shows a slow processing speed compared to the PCA method, and if the planar model is formed incorrectly in the nearby section, the planar model for the subsequent section will also be problematic. And next is Patchwork, the latest study on the ground segmentation. This is based on the concentric zone model, and we process with PCA-based planar modeling with BinWise. This study has an advantage of being robust to changes in the surrounding environment or slopes. However, because the geometrical relationship between the bin is not considered, the planar model may be formed incorrectly. And for this reason, false positive can occur for points that are far away.
I'm Myung-woo Jung, and I'm gonna briefly introduce about our project. Let me start with problem definition. TGS and AOS, which are the main modules of the algorithm, work only in order rather than complement each other. And the algorithm relies on the current scan without the historical information. Next is the contribution for improving the algorithm. We apply the local terrain map which has the historical information without drift, and we applied online traversability map. Lastly, we apply the algorithm to a quadruped robot navigation in complex environment including stairs and slopes. Here is the replication plan. Code for the reference algorithm travel is available. The following header files are improved: TGS and AOS, which are mentioned in previous slide. To improve the travel algorithm, we refer the odometry and mapping algorithm using LiDAR sensor. First one is LeoSam, next robot-centric elevation mapping, and the last traversability mapping. All the algorithms we referred are available. We made our sensor set to adapt the algorithm to a real-world experiment. This is the sensor configuration. Among the sensor set, the LiDAR sensor Auster OS 1-64 model and IMU XSense-MTI-30 model are mainly used. To calibrate the sensors, we use the method of robust real-time LiDAR inertial initialization. And this is the calibration result. These are our platform and the environment for gathering the real-world data. The environment is composed with variety kind of terrain and structures such as the slope and trees. And this is the video of gathering data.
I am Mino O and I will share the improvement method with the comparing result. Firstly, according to the odometry, when to make terrain map by accumulating LiDAR data with the estimated odometry, there should be the errors due to the odometry drift. So to overcome this problem, we add the constraint by traversable grounds matching with the travel on each scan. So this is a framework for our modified LiDAR-based odometry, and this part is modified, and this shows the accumulated data with the travel of ground constraint. And these results are the odometry result of the original LiDAR SLAM and improvement LiDAR SLAM. When estimating the odometry result without the loop closure, there are some performance improvement, like this part, yeah, in here. So by considering traversability in ground segmentation, the odometry can be estimated more accurately. And secondly, according to the terrain mapping, after accumulating data with less drift, we apply travel to split terrain and object. But there are cases where the ground data is determined as an object for a part where TGS-based terrain modeling is not performed near the terrain map boundary. So to overcome this problem, we add a recheck process like this part after AOS by terrain modeling method, which is proposed in the TGS. So these results show the ground and object segmentation results from the accumulated data, and the color data means the clustered object, and this dark green data is mean the terrain data. So you can find these boundaries on the boundaries, the the colored ground data which are estimated as an object in this original table result, but we improved it as shown in here. So by the method as I mentioned before. Okay, and lastly, I will show you the result on the traversability mapping. The problems of the original traversability mapping is from confusing the ground and the ceiling. So, and this misdetermined data make the drift on the elevation mapping again, as shown in here. So there are so many misdetermined data, but with our local terrain mapping, as I shared before, we can overcome these problems. So finally, the travelability map results can be driven by improving travel and LiDAR-based odometry and mapping algorithm, and also by fusing them. So in this, let's see in this part and in this part, the stairs and cars can be detected as a non-travelable area that original travel cannot do stably, with less drift than original one. So we propose the online travelability mapping system for ground vehicle, which can be directly utilized to the autonomous navigation algorithm. But there are some limitations on our algorithm. Our mapping algorithm is loosely coupled system. It means that the odometry, local terrain mapping, and travelability mapping algorithms run in one by one, not as a one algorithm. This problem can be a reason for a high memory usage of onboard PC. So our future work is that make them in one tightly coupled algorithm and that embed path planning algorithm which can be based on our global or local travelability mapping. And lastly, that apply our algorithm to different types of platform and sensors. Thank you for listening. And this is Team 5 with the member Minho Oh, Myung-woo Jung, and Taewon Kim.